In today's presentation video, we will work through the ring of charge problem. The ring of charge problem goes like this. You have a ring of radius A that has a total charge Q uniformly distributed around the ring. You are asked to find the electric field at a point P, a distance x away from the center of the ring along the x-axis. This may seem like a torsion problem, so where do we start? First, let's think of what the equation we might be able to use to solve this problem. We have two ways to solve the problem. First, we have Coulomb's law, and second, we have Gauss's law. Due to the symmetry of the problem, we don't have a nice Gaussian surface to use Gauss's law, so we will use Coulomb's law. Next, we ask if we have all the information that we need to solve this problem. At a glance, it may seem like we already have everything. We have the charge, and by using Pythagoras theorem, we can solve for r. So we are done, right? Not quite. If the ring were just a point charge, we'd be done. However, the ring is a two-dimensional object, meaning that we are going to need to use vector addition to solve this problem. Let's see if we can come up with a more appropriate example. Let's determine the electric field generated by 2 point sources which are located a distance x away from point P along the x-axis and a distance a away from point P along the y-axis. In order to solve two-dimensional vector problem, we must split the vector up into components and solve these components individually. Let's start by determining the y components of the electric field. From the bottom point charge, the component we obtain dkqr square sin theta is positive y direction. The y components of the electric field generated by the top point charge is equal in the magnitude but opposite in direction. Therefore, the total y components of the electric field generated by the point charges experienced at point P is 0. What about the x component of the electric field? The component from the bottom point charge is equal to kq by r square cos theta in positive x direction. The components from top point charge is the same, meaning that we can determine the final electric field by adding them together. However, we are now left with two variables that were not given to us in initial problem, r and theta. We already determined that we can solve for r by simply using Pythagoras theorem. Now that we have r, we can solve this cos theta using simple trigonometric rules. We can now obtain the x component of electric field by plugging these values in. We now have the solution for our electric field. But how does this problem relate to our initial problem? Well, instead of just 2 point charges, what if we had many point charges that will eventually distributed from a ring? As we saw from the previous example, the y and z components of the electric field would be equal to 0 because the symmetry of system would because them all cancel each other out. We are left with an x component of electric field is equal to the sum of all individual x component of the electric field generated by the individual point charges. You can look at the integral and that we will use to determine the electric field and adjust infinite sum of all x components of the electric field generated by infinitesimally small quantities of charge that we will call dq. But we have an integrate that is dependent on dq. How do we define boundaries integration? We need to rewrite in terms spherical variables we can integrate over. In order to do that, we are asked ourselves over dimension can we integrate dq to obtain a total charge q from the ring? The answer is phi. If we sum up all the dq's by going to around ring, in other words by going around the angle phi, we should obtain the total charge q in the end. But how do we write d phi in terms of dq? For this, we come up with the charge density is dependent on phi. Because the charge is eventually distributed around the ring, we know the ratio of charge to angle must be uniform throughout. Therefore, we can say that the ratio of the infinite decimal charge to the infinite decimal angle is equal to the ratio of total charge to the total angle. We can check to see that our charge density is corrected by integrating it over the ring, and indeed we obtain a total charge Q in the end. Now that we have on the charge density, we can write dq in terms of d. Since phi is not dependent on any other variable, and since all other variables are constant, all the variables except for d phi can be taken out for the integral. When we integrate d phi from 0 to 2 pi, we simply get 2 pi. The two pi's in the numerator and denominator cancel each other out, and we are left with our solution. And that is how we solve the classic ring of charge problem.